Welcome to this video on quantum states and wave functions, the language of reality and mastering the micro-world. Classically, we think of particles as definite objects, but in the quantum realm, this intuition fails. Everything is defined by its state, the information that describes it, moving beyond the concept of simple objects. We begin with part 1, the state. This involves defining the fundamental list of possibilities for a quantum system. A quantum state holds complete information about a system. It allows for superposition, a weighted mix of classical outcomes. Reality at this scale is information, like a line of code. Next, we move to part 2, the wave function, where we meet the symbol psi or $psi. The wave function, $psi, is the mathematical function that represents the quantum state, serving as the information container. It depends on space and time, and holds the secrets to a particle's potential location. Visualizing $$ means seeing a probability cloud, not a single point. Where the cloud is densest, the particle is most likely to be found. This cloud is the physical reality of the state before observation. Part 3 is about the Born rule, which connects the underlying quantum mathematics to what we actually observe in the physical world. Max Born's vision showed that the wave function $psi itself is not the probability. Instead, the square of its magnitude gives the probability density, turning abstract math into a successful physical theory. The total probability of finding a particle everywhere in the universe must be 100%. Math calls this normalization. For any existing particle, its existence is mandatory. In part 4, we delve into phase and rotation, exploring the secret life of complex numbers in quantum mechanics. Wave functions use complex numbers to store phase, which can be visualized as a rotating arrow. This phase dictates whether two wave functions add up or cancel out, leading to the phenomenon of interference. Part 5 focuses on the engine of quantum evolution, Schrodinger's equation. The Schrodinger equation is the master rule of the quantum world, describing how the wave function $psi changes over time. This evolution depends entirely on the energy or Hamiltonian of the system. Energy eigenstates are stationary states that do not change their probability density over time. They have specific, quantized energies, which explains the stability of atoms. Any complex state is built from these components. In part 6, we explore confinement, often demonstrated using the concept of the particle in a box. When a wave function is trapped, it forms standing waves, similar to a vibrating guitar string, and can only exist at certain frequencies. Higher energy states feature more nodes, which are points of zero probability. A trapped wave function can never have zero energy. This is called zero-point energy. Everything is always vibrating, a phenomenon known as the quantum jitter. Part 7 introduces the tunnel, where quantum particles perform the seemingly impossible task of breaking through walls. Quantum tunneling occurs when a wave function leaks through a thin potential barrier instead of bouncing back. This allows particles to cross classically forbidden gaps and is essential for processes like the sun's burning. Finally, in part 8, we look at observables, which is the process of turning abstract quantum states into measurable facts. The act of measurement causes the wave function cloud to instantly collapse into a single dot, losing superposition. While we cannot predict a single result, we can accurately predict the average of many measurements. To summarize, the core revolution is that at the fundamental level, physics is information. The wave function $psi holds all knowledge of a system, and reality is governed by the Born rule of probability, not certainty. The stability afforded by quantized states makes atoms and life possible. Thank you for watching this video. We invite you to join the quantum frontier.